Hello and welcome back to MathandBolt. So we'll continue uh, with solving differential equations by using the method of variable separation. So here we have the first problem. So let us begin. So we begin by first rewriting the differential equations as x times dy over dx equals to, we'll take the second term to the right hand side. So that should give us negative cotangent of y. Now I multiply both sides by dx, that means separating the differentials. We have x times dy equals to negative cotangent of y times dx. So one next step will be to make the coefficient of dy entirely a function of y and coefficient of dx purely a function of x. So that means we need to divide both sides with the product x times cotangent of y. So that should give us dy over cotangent of y equals to negative dx over x. So for the term on the left hand side, we have 1 over cotangent of y, which is simply tangent of y dy equals to negative 1 over x times dx. So here we can see that the coefficient of dx is negative 1 over x, which is purely a function of x, and the coefficient of dy is tangent of y, which is a function of y only. So what we can do, we can integrate both sides. So let's do that. So integration of tangent of y, so let me write down the formula. So here we're going to use the formula, that integration of tangent of u du, so that's equals to natural log of the absolute value of secant of u plus the constant of integration c. And for the integration on the right hand side, we have du over u, which is equals to natural log of u plus the constant of integration c. So let's perform the integration. So we should get natural log of, so here the variable is y, so that means we'll have secant of y equals to negative log of the absolute value of x plus the constant of integration, which comes from both the two integration. But instead of using c, we will be using natural log of c, which will become evident in a moment. So let's bring the first term on the right hand side to the left hand side. So we have natural log of secant of y plus natural log of x, and that will be equals to log of c. So we can use the property here, the property being log of a plus log of b. So that's equals to log of a b. So for combining the two terms on the left hand side, we have natural log of x times secant y, which is equals to log of c. And because we have logarithm on both sides, so we can get rid of the log, and that was the only reason why you used log c instead of c. But that means we have x times secant of y is equals to c, and we'll take the secant of y to the right hand side. So that means we need to divide both sides by secant of y, so that will be c over secant of y, and 1 over secant of y, that's simply cosine of y. So that means our final solution will be x is equals to c times cosine of y. So we have written the solution of in terms of x as a function of y. So this is the required solution to our given differential equation. Let's move on to the next problem. So problem number 2. So here we have the following differential equation. So let's try to solve it. So we begin by rewriting the differential equations as, so we're going to do is multiply both sides with cosine of y. So that gives us cosine of y times dy over dx. So that's equals to x times e raised to the power of x times natural log of x plus e raised to the power of x divided by x, or simply cosine of y times dy. So now we multiply both sides with dx. So the first term will be e raised to the power of x times natural log of x. The x and x has cancelled out, plus e raised to the power of x divided by x, all multiplied to dx. So both sides, when you look at both sides, we'll see the coefficient of dy is entirely a function of y, and the coefficient of dx is purely a function of x. So that means we can integrate both sides. Integration of cosine function will give us sine of y equals to integration of e raised to the power of x times natural log of x dx plus integration of e raised to the power of x divided by x dx. Now what we will do, we will only integrate this first integral on the right hand side and will not integrate the second integral. So let's begin with this integral. So here we have the product of two functions, e raised to the power of x times natural log of x. So that means we need to integrate by parts. Integration e raised to the power of x times natural log of x dx. So we'll consider log of x as the first function and e raised to the power of x as the second function. So that means u will be equals to log of x, such that when we differentiate both sides with respect to x, we should get du is equals to dx over x. Next we have e raised to the power of x dx. So that will be equals to dv, such that when we integrate both sides and solve for v, we should get e raised to the power of x. So let's apply the by parts formula. So we have e raised to the power of x natural log of x dx. So that simply equals to uv minus integration v du. So we have u times v. So u times v will be e raised to the power of x times natural log of x minus integration. So we have v. So v is e raised to the power of x and du is dx over x. So let's use this value and replace it here. So that gives us integration. We have e raised to the power of x natural log of x minus integration e raised to the power of x divided by x dx plus the integral e raised to the power of x over x dx. And we see that here immediately the second integral and the third integral cancels out. And also we need to use the constant of integration c. So hence our final solution will be sine y equals to e raised to the power of x times natural log of x plus the constant of integration c. This is the required solution. Let's move on to the next problem. Problem number 3. Let's begin by simplifying the two terms on the right hand side. So we have dy over dx, that's equals to e raised to the power of x plus y. So that can be written as e raised to the power of x times e raised to the power of y plus e raised to the power of y times x cubed. So that means we can take e raised to the power of y as the common factor. So that will get multiplied to e raised to the power of x plus x cubed. So now multiplying both sides with dx, that means separating the differentials, we have dy is equals to e raised to the power of y times e raised to the power of x plus x cubed dx. Now we want to take this e raised to the power of y to the left hand side, so we'll multiply both sides with e raised to the power of negative y. So that will be equals to e raised to the power of x plus x cubed dx. Now we see that the coefficient of dx is purely a function of x and the coefficient of dy is purely a function of y. So that means now we can integrate both sides. So we have integration of e raised to the power of negative y dy, and that's equals to integration of e raised to the power of x dx plus integration of x cubed dx. So integration of the exponential function gives us the function itself. So we have e raised to the power of negative y. Now since we have a negative here, so that will give us a negative e raised to the power of negative y, which is equals to e raised to the power of x plus x integration of x cubed, so we use the power rule. So we have x raised to the power of 3 plus 1 divided by 3 plus 1 plus the constant of integration c. Let's call it c prime for the time being. So we have negative e raised to the power of negative y equals to e raised to the power of x plus x raised to the power of 4 all divided by 4 plus c prime. Now we'll write all this term and this particular term together. So we have e raised to the power of x plus e raised to the power of negative y plus x raised to the power of 4 over 4, which is equals to negative c prime. So negative c prime will be c. So that means here we have used c is equals to negative c prime. And this is the required solution to our given differential equation. Let's move on to the next problem. So we have the differential equation. Let's try to separate the differentials first. So we have square root of 1 plus x squared multiplied to dy. We'll take the second term to the right hand side. So we have negative square root of 1 plus y squared multiplied to dx. Now since we have the coefficient of dy as some function of x, but we want it as a function of y instead. Similarly for the coefficient of dx, so we will divide both sides with the product square root of 1 plus x squared times square root of 1 plus y squared. So we have dy divided by square root of plus y squared equals to negative dx over square root of 1 plus x squared. Now we have the coefficient of dx, which is negative 1 over square root of 1 plus x squared, purely a function of x. Similarly, the coefficient of dy is purely a function of y. So that means we can integrate both sides. Now integration of dy over square root of 1 plus y squared. So that will be, we'll use the formula here. Let me write it down. So we have integration of du divided by square root of a squared plus u squared. So that's equals to the natural log of u plus square root of a squared plus u squared plus the constant of integration c. So we'll use this, and this should give us natural log of y plus square root of 1 plus y squared equals to negative times natural log of x plus square root of 1 plus x squared plus the constant of integration c. But since everything is in terms of logarithm, we have natural log of c. Now we will take this first term on the right hand side to the left hand side and combine both of them together using the property of logarithm to get natural log of y plus square root of 1 plus y squared multiplied to x plus square root of 1 plus x squared, and this is equals to natural log of c. Now we can get rid of the logarithm. So that will give us y plus square root of 1 plus y squared or multiplied to x plus square root of 1 plus x squared, and this is equals to the constant of integration c, and this is also the final and the required solution to our given differential equation. Let's move on to the next problem. So here we have another differential equation. So let's try to solve this. So we will begin by separating the differentials. For that, let's cross multiply the terms. We have y times 2 term log of y plus 1 multiplied to dy equals to e raised to the power of x sine squared x plus e raised to the power x sine 2x whole multiplied to dx. So since the coefficient of dx is a function of x and that of dy is a function of y, we can now integrate both sides. Let's do that. So the first integral will be 2 times integration y log y dy plus integration y dy equals to integration e raised to the power of x sine squared x dx plus integration e raised to the power of x sine 2x dx. So let's label this as number 1. So we have 4 integrals that needs to be computed. So we'll compute the first integral on the left hand side and the integral on the first integral on the right hand side. So let's start with the first integral. So we have I1 equals to 2 times integration of y log y dy. So here we have the product of two functions y and log y. We'll use integration by parts. So let's assume that let u be equals to natural log of y, such that when we differentiate both sides with respect to y, we get du is equals to 1 over y dy. Then we will consider y dy, so that's equals to dv, such that when we integrate both sides and solve for v, we get v is equals to half y squared. So we have now 2 times, so integration of y log y dy, so this will be u times v. So we have u times v minus integration of v du. So v is a half y squared times du. So du is 1 over y dy. Right. This equals to 2 times half y squared natural log of y minus half integration. So 1y will get cancelled out from the numerator and 1 from the denominator. So that gives us y dy. So if we multiply throughout by 2, so that will be y squared natural log of y minus 2 times half, that will be 1. But we have integration of y dy, so that will be half y squared plus some constant of integration. Let's call it c1. So this is a integral I1. Now we'll move on to the second integral. Now integral e raised to the power of x times sine square x dx. So let's suppose that u is equals to sine squared x, so that when we differentiate both sides with respect to x, that gives us du is equals to, so in differentiation of sine squared x is 2 times sine x times cosine x dx. Here we have used the power rule as well as the chain rule. Now this is an identity, 2 times sine x cosine x, which is sine 2x dx. And we will consider e raised to the power of x dx. So that will be dv, such that when integrate and solve for v, that we get e raised to the power of x. So this will, as this integral by parts, will be u times v. So our u is sine squared x multiplied to v. V is e raised to the power of x minus integration v du. So v is e raised to the power of x times du. So that is sine 2x dx plus some constant of integration. Now let's substitute this value back to our equation number 1. So equation number 1. So we have this entire thing as I1. So this will be y squared natural log of y minus half y squared plus the constant of integration c1. Then integration of y dy, so that's half y squared plus the constant of integration c2 equals to, this is the integration of this is the integral I2, so that's e raised to the power of x times sine squared x minus integration of e raised to the power of x sine 2x dx plus the constant of integration. So this will be C3. I've already used C2 plus integration e raised to the power of x sine 2x dx. So there are a couple of terms that will get cancelled out. So the second and the third term on the left hand side, and similarly this term and this term gets cancelled out, and our final result will be y squared natural log of y equals to e raised to the power of x times sine squared x plus the combined constant of integration of all the constants of integration, giving us c, and this is the required solution to a given differential equation. Let's move on to the next problem. Let us solve this differential equation. We begin by separating the differentials. So for that we will be cross multiplying. We'll have x times 2 natural log of x plus 1. So that get multiplied to dx equals to sine y plus y times cosine of y will multiply to dy. But clearly we can see here that coefficient of dx is a function of x and coefficient of dy is purely a function of y. So that means that we have variable separation. Now we can integrate both sides. So we have 2 times x natural log of x dx plus integration dx, which is equals to integration sine y plus integration y times cosine y dy. Now this particular integral we have already performed in the previous problem, except for the fact that x was replaced with y. So the result will nonetheless be the same. So we will get x squared natural log of x minus half x squared plus integrating dx. So that will give us, as this is x dx, the integration of x dx, so that will be plus half x squared plus some constant of integration c, but that will be taken care of later on. Then we have integration of sine y, so this is dy, which will be equals to negative cosine y plus integration of this particular integral, which we'll have to perform by part. So let's call it I1. We'll label it as equation number 1. Fine. So let's suppose that here we will consider y as the first function and cosine of y as the second function. So that means u will be the first function y, which gives us du equals to dy, and we'll consider cosine of y dy, so that will be our dv, such that when we integrate both sides and obtain the value of v, we should get v is equals to sine y. Okay? So that means our integral I1 will be equals to u times v, so that means y times sine y minus integration of v du. So our v is sine y times du, so du is dy here. So that gives us y sine y minus integration of sine y, so that's negative cosine y plus a constant of integration, which is equals to y sine y plus cosine y plus a. So let's substitute back this to our equation number 1. So we obtain in our equation number 1, we have negative cosine y plus I1. So instead of I1, let's substitute this with plus y sine y plus cosine of y plus the constant of integration a. Now immediately we see that some of the terms will get cancelled out. So this 2 terms and negative cosine y and positive cosine y gets cancelled out, which leaves us with the final solution x squared log x equals to y sine y plus the constant of integration c. So this is the required solution to the given differential equation. Let's move on to the next problem. So let's begin by rewriting the given differential equation as 1 minus x squared times dy. So we'll take the second term to the right hand side, x y squared dx minus xy dx. So what we can do, we can take dx as the common factor from both the two terms. Can get rid of this dx. Then we have 1 minus x squared dy equals to, so from xy squared and xy, we can take xy as the common factor, leaving us with y minus 1 dx. Now we are going to divide both sides with 1 minus x squared times y minus 1. So that means on the left hand side we have dy over y minus 1 equals to, on the right hand side we have x dx divided by 1 minus x squared. Now this is in the variable separable form. So let's integrate both sides. Fine. Now to integrate the integral on the left hand side, we have to use the method of partial fractions. So I hope you're familiar with the method of partial fractions. So that means I'll simply write down the result. So 1 over y times y minus 1. So that can be written as 1 over y minus 1 minus 1 over y dy. And here we are going to, for the integral on the right hand side, we are going to integrate by using the method of substitution. So we multiply with negative half, and then we also have to multiply with negative 2 in the numerator. So we have negative 2x dx divided by 1 minus x squared. Right? Okay, so our integral will be, so we have integration of dy over y minus 1. So that's natural log of y minus 1 minus integration of dy over y. So that's log of y equals to negative half log of 1 minus x squared plus the constant of integration c, and this is our final solution. So let's solve this differential equation. We rewrite it as tangent of y dx equals to, so we'll take the second term to the right hand side. We have negative secant squared y times tangent of x dy. So our goal is to make the coefficient of dx purely a function of x and coefficient of dy a function of y only. Means we need to get rid of this tangent of y from the left hand side. So we will divide with tangent of y times, and we need to get rid of this tangent of x on the right hand side. So we'll divide by tangent of x. So that should give us dx over, so we have tangent of x equals to negative secant squared y divided by tangent of y dy. So we have 1 over tangent of x on the left hand side. So that's simply cotangent of x dx equals to negative secant squared y over tangent of y dy. So this is now in the separable form. So that means we can integrate both sides. The integration of cotangent of x, so that's simply natural log of sine x equals to negative. Now for the integral on the right hand side, we need to use the method of substitution to get natural log of the denominator, which is tangent of y plus some constant of integration c, but everything being in log will take natural log of c. Now we'll bring the first term on the right hand side to the left hand side. So we have natural log of sine x plus natural log of tangent of y, and that is equals to log of c. So here we can combine these two terms as log of sine x plus tangent of y. This is using the property of logarithm, which will be equals to log of c, and getting rid of the logarithm gives us finally sine x times tangent of y equals to c. So let's box it. So this is going to be the final solution to our given differential equation. Let's move on to the next problem. So let us begin by separating the differentials. We have 1 plus x times 1 plus y squared dx. Now let's keep it on the left hand side. and we'll take the second term to the right hand side. We have negative 1 plus y times 1 plus x squared dy. Now we will divide both sides. That means we need to get rid of this 1 plus y squared on the left hand side and 1 plus x squared on the right hand side. So we're going to divide the overall equation at 1 plus y squared and 1 plus x squared. So that should give us 1 plus x divided by 1 plus x squared dx equals to negative times 1 plus y whole divided by 1 plus y squared dy. So this is now in the separable form. That means we can integrate both sides. We can further rewrite this equation as 1 over 1 plus x squared. So this will be dx plus integration x dx divided by 1 plus x squared equals to negative integral dy divided by 1 plus y squared minus integral y dy divided by 1 plus y squared. Now let's integrate each of the integrals. So we're going to use the formula from the table of integrals. Integration du over 1 plus u squared. So that's equals to the arctangent of u, or the tangent inverse of u, plus the constant of integration c. And to integrate this second integral and this particular integral, we're going to multiply and divide by 2. We have half 2y, so that we can use the method of substitution, and we should get tangent inverse of x for the first integral. For the second integral, we have half natural log of 1 plus x squared equals to minus tangent inverse of y minus half natural log of 1 plus y squared plus the constant of integration c. So let's rewrite the terms to get tangent inverse of x plus tangent inverse of y plus half natural log of 1 plus x squared plus half times natural log of 1 plus y squared, and that is equals to the constant integration c. So this is the required solution to a given differential equation. So let's move on to the final problem. So here we have the differential equation given by tangent of y times dy over dx equals to, so here we have this expression which is the sum of two trigonometric functions. So let's apply the formula sine A plus sine B. The sum of trigonometric functions is equals to 2 times sine. So we have A plus B divided by 2 multiplied to cosine of A minus B over 2. So that we get tangent of y times dy over dx, that's equals to, so we have 2 times sine, so x plus y plus x minus y, so x plus y plus x minus y whole divided by 2 times cosine of, so we have a minus b, so that's x plus y minus x plus y whole divided by 2. So this should give us 2 times sine. So here we'll see that y and y will get cancelled. So we have 2x in the numerator divided by 2. So that's sine x times cosine of. So we have x and x cancelling out. So we have 2y over 2. So that's simply y. So now what we can do is we can separate the differentials. So we have tangent of y times dy, and that's equals to 2 times sine of x times cosine of y times dx, and we want to get rid of this cosine of y, so that means we'll take it to the left hand side by dividing both sides by cosine of y, or we can simply multiply with secant y. That means we get secant of y times tangent of y dy, and that's equals to 2 times sine x dx. So this is in the separable form. So that means we can integrate both sides. Now integration of secant y times tangent of y. So that's simply secant of y, which is equals to, so we have 2 times integration of sin x ds. So that's negative 2 times cosine of x, since integration of the sine function gives us negative cosine x, plus the constant of integration c, or we can simply write it as 2 times cosine of x plus secant of y equals to the constant of integration c, and this is going to be the required solution to our given differential equation. Thank you.